inviting me to speak. So this is, I guess, like a work in progress at the moment. So I'll start with the following general question. So suppose you have a fibration of compact symplectic manifolds. Okay. And then so I guess what you want to try to do is do Floer theory in E and have it depend on something along the lines of B and F. So given some Lagrangian in B and some Lagrangian in F, can we construct L in E, which fibers over with which fibers over LB with fibers LF. Okay, so kind of a general thing. This is kind of more. This is going to this sort of construction is going to be ad hoc in most cases. Ad hoc. Okay, and then B, and then so assuming that you can kind of get this to work out nicely. Where this is going to be the same projection here, how to compute. So can we define H of L? And should this be given in terms of? So this is a question. Should this be given in terms of HF LB, HF LF? Okay, so that's kind of the starting point for this particular result. And then so I guess the first example that I want to focus on, so main example. Can people see this? Yeah, okay. So if you take full flags in C3, over here. Okay, so if you forget, you have a chain of subspaces of increasing dimension, and if you just forget the top dimension, if you forget the two-dimensional complex vector space, you get a fibration over P2. And then the fiber is going to be P1. Okay, so if this should work out, it should be in this situation. This is sort of the nicest possible where these are, if we pick the right Lagrangian, it's going to be monotone. Okay. Okay, and then so flag itself has an inherent symplectic form, but let's give. So let's give flags the weak coupling form. Okay, so this is going to be of the form A plus K pi star omega B. So we'll say omega B is just the Fubini studio form. Okay, so K large enough, dA is 0. And then so some results of Gilman, Lehrman, Sternberg. So given, what do I want to say here? So given a symplectic connection, we'll say TF plus H. on E, there is a recipe. I don't know how to spell recipe. I'm really bad at spelling. That's receipt, right? Okay. Recipe? Is that it? Yeah, okay. Thanks. Ask the audience. Okay, so there's a recipe for constructing A. Okay, and then I guess furthermore, I'm assuming that the holonomy on this connection is going to be Hamiltonian with respect to the fibers. Okay, so you have this nice, so H here. Oh, I guess I haven't told you exactly what A is. So constructing A, the form such that, let's see, if I restrict to a fiber, it's just going to be the thing that I want. And dA is closed. And H is going to be, so it's fiber-wise symplectic, and then so you can define H to be the perp of TF with respect to A, and gives you a nice symplectic connection. Okay, so this is the setup. So that's what I want to give. That's the kind of symplectic form that I'm talking about on this E here. Just because it makes things easier. If it's going to make things easier if the projection is going to be compatible with the form. And then this K here, so the problem is that A might degenerate in the horizontal direction. So if you pick K large enough, so in some sense, if you make the fiber small enough, then this is actually a non-degenerate form.
So this is also coincide with, like, if you think of like C3 as a symplectic reduction, it's also something from the Euclidean spacement.
From the co-adjoint orbit sort of thing. Yeah, I guess I imagine that it's going to be the same up to rescaling on the fibers.
Can you remind me,
Mm-hmm.
The existence of such a form A is equivalent to the vibration being Hamiltonian, or there's a slight difference?
It's what is it? You're right. It's equivalent to the holonomy of the fibration being Hamiltonian on the fibers. Yeah. Okay, so it works out in this case because H1 of P1 is 0, so any symplectic action is going to be Hamiltonian. Yeah, yeah. Okay. Let's see. Okay, so now, so in flag 3, so I guess the idea is, if there's any hope for this to work, we'd want to like pick something that fibers over the Clifford torus here. We try to pick a Lagrangian which fibers over the Clifford torus. Okay, so the barycenter of this guy. Okay, and then so it's more of this like symplectic vibration theory from Gilliman, Lerman, Sternberg. So on pi inverse u, where let's just say the Clifford torus is contained in some neighborhood u, so the U isn't going to contain any of the singular points of the toric fibration. There is a symplectic isotopy so that let's say E restricted to cliff 2 is symplectically just P1 cross cliff 2. Or really, what the result is actually saying is that the moment map for T3 mod scaling action is phi circ pi. So phi is going to be the moment map for P2. Okay, so you can kind of adjust the connection on a neighborhood here, such that the moment map for this natural T2 action is just project down to P2 and then take the moment map for that. Okay, so this kind of gives you a sort of symplectic trivialization on on a level set of the moment fiber.
Isn't that P1 bundle like projectivization of some rank bundle? Yeah. So then this is somehow like saying that the Cherenkov loss of restriction to the torus is 0. Yeah, but that's automatic. I'm saying like it's kind of trivial, isn't it? And such as like trivialization is.
Depends on what category. If it's a symplectic trivialization, there might be a geometric condition.
Okay, so idea. So L is going to be some section of Cliff 1s over the Clifford 2 torus. Okay, and then so I still haven't quite worked out how many there are of these. So there's at least Z. We'll say U1 bundles over T2 by some clutching construction. Okay, and then so how many of these you can actually realize inside of this trivial product, I am not sure.
Sorry, what do you mean by clutching in this context?
Sorry?
What is clutching?
Oh, like so how many U1 bundles are there over T2, at least topologically? And then so you have, so you would remove a small neighborhood here, and then so that retracts onto, yeah, so this clutching construction.
But that doesn't tell you how this is inside flat space. You just ask about topology.
Yeah, exactly. I'm not sure. I mean, there's at least one, so that's good. Okay, and then so.
Can they all be realized as Lagrangians inside flat space?
So anything that we pick here is going to be Lagrangian since it's symplectically just this.
No. I mean, if you fix only if it's the trivial U1 subbundle. If you take a product symplectic form, then which circle you pick inside the P1 fiber is not allowed to move. Otherwise, it sweeps symplectic area into fiber. And you need to change the horizontal distribution each time. You need to show that it's possible, right?
But on the, yeah, so I suppose in this, and in this trivialization. I mean, the symplectic form. It's the
symplectic form? What's the symplectic form?
So it's just going to be.
Yeah. So how do you do any kind of clutching with this?
Well, I mean, anything in the horizontal direction is just like there is no contribution.
Yeah, but the horizontal distribution is just identity of P1.
Yeah.
So you can't clutch. If you pick once you pick the U1 circle in one P1, you have to keep the same one everywhere over F2.
I don't quite see it. That's fine.
It's not going to be Lagrangian.
Okay. I mean, you buy that there's at least one, right?
Yeah, that's exactly one.
Okay. Okay. That answers that question.
Okay, I thought you were planning to have a Z off.
No, I wasn't.
Oh, you're only planning to do one. Okay, there is one.
No, but you answered my question. I was wondering about this, and now I know. So, yeah. I mean, we're just working with this one here. Okay. Okay. Yeah, I try to ask the audience, right? It's like farming out my questions.
But you should be able to build more, just you have to be more clever.
From this construction, I mean, I don't know. We could talk about it. Talk about it after. Okay. Okay, so right, and then so can we even in any sense? Right, and then so you need the usual transversality and compactness results. Okay, so the idea here. So for the general theory to work, so B is rational. In the sense that the class of omega sub B lives in H upper 2 of B with rational coefficients. Okay, because you really, so the type of scheme that I'm going to be using on the base is this Shelley-Bach-Monk thing. So use a divisor such that the homology class is like some large multiple of the Poincare dual of this to achieve transversality and compactness in the base. Okay, and then so the fibers are going to be fibers monotone. Okay, and then so is this a chalkboard?
Yeah.
Oh, okay. Maybe I'll go over here.
There's another one behind. Yeah, one behind it.
All right, okay. So, okay, so let's just count some things. So we'll say L. And then, so I'm going to take basically trajectories, which might have marked points, which map to pi inverse of this divisor, say, to stabilize, and then with some output in inputs. Okay, and then so you kind of want to choose things nicely. So idea, use almost complex structure of the form, we'll say JF, K, JB, 0. So some sort of upper triangular with respect to this connection. Okay, so this is going to be the pullback of some form on the base, so it's going to be constant along the fibers, and then K, JB allowed to be domain dependent. So a la Chelly-Bach-Monk and then Charest Woodward. So this is 07, I think, right? Yeah. 14, 15. So Charest, Woodward, I think it's 15.
So you have to choose some worst function. The worst function doesn't have to respect the fibration.
You want to choose it in a nice way.
It's mostly on the Lagrangian in a way. It's on the Lagrangian, and you probably will want to practice the project.
Yeah, so you want to pick it of something like, so you have B, more smell on LB. And then so you have critical fibers, so like, let's say critical fiber. And then so you want to kind of construct your F to be the pullback of B, but then you have these whole fibers which are singular sets. And then in a neighborhood of each critical fiber, you kind of multiply by a bump function times some Morse function G for, so GI from LF to R Morse. Okay, so something like this, so that you have basically, what's the picture? So say you have a torus, and then you have, say, circle fibers. You can pick the usual Morse function on the base, and then in the neighborhood of each critical fiber, you want to like multiply by a bump function and then add on something that's Morse for each fiber. Okay. So yeah, you do want to have something that's a bit adapted to the projection. Okay, and then so you define, so mu n, x1, xn. So this is going to be, maybe I should start this on a new board. So -1 to something, and then you have some sort of sign. So summing over holomorphic configurations in some zero-dimensional moduli space. xn, okay, with output x0. And then you have to keep track of energy, so let's keep track of the energy of when I project down to the base, and then have some remnants of what the fiber energy is. So this is going to be total minus maybe some epsilon energy pi OU. And then so times x naught, the output. Okay, so this is, say, in Novikov ring with positive powers. So you can choose this epsilon. Choosing this epsilon so that this is positive is really just equivalent to saying that, where did I write that? This weak coupling form, yeah, I erased it. So you have this weak coupling form. And then so this is going to be symplectic for k large enough. And then so certainly I can make this symplectic as well if I pick epsilon small enough. Okay, so still working out the bugs in this, but I think I want something like this here. And not just like something so ham-handed as the total energy. Okay, so this these composition maps. Okay, so theorem. These composition maps are well defined and satisfy A infinity axioms. Okay, so that's kind of, I mean, that's really just the statement about transversality and compactness. Okay, so, right. Right, but then, so I started off the talk asking about what would you do, how would you define, Floer homology, right? And then so, in the classical case, when you have some sort of fibration, you say filter by say, Morse index of projected critical points, right? And this gives you this Leray spectral sequence. Okay, so we're going to do the same thing here. You filter by this term here, this Q degree. Okay, so in the event that mu1 squared equals 0, or some u1 sub b squared equals 0. So for some weak bounding cochain, so if let's say L is weakly unobstructed, then filtration by E pi OU induces a spectral sequence. Okay, and then so you sort of check that it at least converges to something, and that something, you want to check that that something is actually what you want it to be. So theorem, this spectral sequence we'll say, call it E sub t, converges to HF, L, but with Novikov Q and R coefficients. Okay, or at least it converges to the the homology of a chain complex, right? So we haven't seen that it's like a symplectomorphism invariant or Hamiltonian isotopy invariant yet. Okay, and then the second page is, let's say, essentially the homology of this chain complex. We'll say CFL with differential something along the lines of dB Morse. So this should be dLB Morse plus or minus the Floer theory of the fiber. Okay, so annotate. So this is the sort of thing, once you see something like this, you can kind of think about this Leray spectral sequence where you filter by base degree of the critical points. And then so this second page here, if you have any hope of computing it, so E2 is computed via usual Leray Serre spectral sequence. We'll say ELS T, and then E2 of that it's going to be the regular cohomology of the base with coefficients in some local system for the Floer cohomology of the fiber. And then so you have some sort of grading arising from the filtration. Okay, so then this is a lot. Essentially, I'm saying that I have a spectral sequence whose second page is computed via another spectral sequence. But in nice cases, it breaks down and you can sort of compute some things. So let's see, maybe, right, so special cases. Some special cases. Okay, so when the base is monotone, so this is kind of a work in progress. So when LB is monotone, and our fibration is fiber-wise scalar. So F, there's the picture, is scalar. Then you would hope, at least in this case, that U1 squared is equal to 0, so that the Lagrangian is unobstructed. And here I'm also assuming, so this is from my whole talk, that LF is also monotone. Okay, and then so the idea is that in this transversality scheme, you can kind of use almost complex structures of the form of some block diagonal with respect to the symplectic connection. We needed something here in the general case when we had multiple covers and also when the differential in the vertical direction might have vanished. Okay, but in this case, because of the Kähler assumption, so only need this non-zero when configuration vertically constant. But then in that case, there's like this Oka principle that says if you have something in the base, so this is, let's say this goes to B comma LB, we can lift this to a vertically constant disk. In some, we'll say, if say the J is integrable. Okay, and then once you have that, you can sort of perturb it a little bit, and then this is going to be regular, at least this particular configuration, and then you can perturb it a little bit so that it kind of matches up with some perturbation data that you already picked. And then it's going to persist just because these two moduli spaces are regular, compact, and so they're compact cobordant. So there's going to be some sort of bijection for small enough perturbation. And so that's basically the sketch of this here. In some sense, it just kind of starts you off there. And then so now can we compute, let's say HF of L, where L is this thing that I had down earlier. So this is a subset of P1 plus Cliff2. Okay, so I mean, if you like, we can say, suppose it's a trivial one for now. And then so the idea here, I lost my spot. Okay, so if L is trivial, or trivial enough, we can say that this coefficient system in the theorem is just constant over here. And then so that means that E2LS should just be the tensor product of the two homologies. Okay, and then with some tensored with some graded thing. Okay, so this kind of gives you a little bit of hope for this sort of thing. Any questions so far? Okay, and then so work in progress. Let's say, so it remains to see that the differential after E sub 3 is equal to 0. And then so, and then you kind of hope that, so this along with some symmetry arguments. Should gives you that HF of L is just going to be the tensor product of the two. Okay, so that's kind of what I'm working on right now. We already kind of knew this. Let's see, main theorem. So we already kind of knew this. There's like this Nishinu, Nohara, Ueda, and I think it's 09 maybe. There is at least one non-displaceable, we'll say Floer non-trivial. Lagrangian of this form. So you kind of expected this to happen, but then this sort of machinery, you can apply it to more things. I'm going to have to pick Denis' brain afterwards about how many of these sections of Cliff 1s can we find here that are actually Lagrangian. Okay, so this sort of thing. Any questions?
You say that the infinity algebra also splits.
I'm not sure. There's this, I think, Amorim 14. He does this like A infinity algebra for the product case. But it's not so clear to me in this context why it would. Okay. What'd you say?
Why do you know? Sorry, so you state that things degenerate after the third page.
That's in progress.
But what's the reason why?
The reason why I expect it, it's essentially using this like this monotonicity of the base, right? So you know that in the Floer differential for the base Cliff 2, the maximal Maslov index disk showing up is 2, right? And then so I kind of want to take that guy and somehow lift it using this like modified version of an Oka principle and somehow compare it to something else showing up.
But how many lifts do you expect to have?
I mean, there's at least one.
Okay.
Yeah.
I think I agree with the intuition.
Yeah. So heuristically, that's kind of what I expect.
Sorry, did you say the assumption is like the fibers are monotone, right?
Mm-hmm.
You just said that like in that result, you also need the base is monotone.
Yeah, that's right. So thank you for the questions. Okay, and then so second application. Okay, so you kind of want to write down we'll say some sort of mu 0. What's my notation? Is it superscript? I think it's superscript. Mu 0 for L. In terms of, let's say mu 0, this is for L, this is for LB, and mu 0 LF, right? So this sort of, you kind of want to express the potential for LF in terms of something from the base and the fiber. Let's see. Okay, so again, let's just assume for now LF and LB are unobstructed, or maybe weakly unobstructed. Okay, so at any rate, we'll just go with that for now. Right, and then so you can say I keep erasing things. So define the leading order potential for L. So this is going to be, let's say, W upper 0 sub L, and the variable it's going to depend on is going to be a representation. So rho is going to be in we'll say pi 1 of L into, we'll say, Novikov ring with two variables. Okay, so essentially I'm just going to take the mu 0 part of this A infinity algebra and just take the terms which are of degree 0 in Q and which have minimal degree in Q. So this is kind of what you expect. So U such that E pi O U equals 0, and then U such that the energy of pi circ U is the min over energy of pi of V not equal to 0, and V has some output, is isolated with some output x. Okay, and then so it's just basically, I have some sort of holonomy, maybe I didn't write that down before, holonomy, and then Q e to the pi circ U are e to the U minus epsilon e to the pi circ U. And then whatever output decides to show up there. And then I think there's going to be a sign as well. Okay, so I think in my original A infinity algebra I didn't really include this holonomy term, but I wanted to. I just didn't write it down. Okay, so it's really just the stuff that has Q degree 0 and has Q degree minimal for each generator in CFL. Okay, and then so theorem, we'll say the leading order potential at a representation rho. So that should really include everything from the fiber. So LF, and then the representation induced from that, plus the leading order for the base, which is what it usually is. Okay, so phi O L And then I'll explain what this L is. Okay, so first I'm going to say something about, like, the eventual hope. Eventually. Critical point for L, or critical point for W rho L implies that the Floer cohomology is isomorphic to the usual with Novikov coefficients. Okay, and then so this formula gives you some sort of hope for actually computing the derivative of this with respect to the variable, the representation variable. Okay, so here, L. No. Let's see. So the tangent space of say, the space of representations, so this is, say, at any point rho, this is going to be naturally just h upper 1 of L. So what I really mean is units here, and this is just in the full ring. And then so by critical point, I mean so the derivative of W0L at rho as a map from H1 L lambda into, we'll just say the chain complex for now, is 0. That's what I mean by that.
But, I mean, if you have a critical point for sort of the leading order part of a function, that might not mean the same point as a critical point for the function.
Yeah, it might be something else, right?
Okay, so you might have to change
For some other, say, alpha or something. So alpha. Yeah, because it's like this, like you like solve for alpha like order by order or something, right? Okay, and then so this lifting, this L, this is like this sort of, when the fibers are Kähler, you can use like an idea. You can use an idea of Donaldson, and you can sort of trivialize the pullback. So use heat flow by Donaldson. And then I forget what year this is, 90, this might be 96. So for U, we'll say a J sub B holomorphic configuration, so you can consider the pullback U star E is trivial with respect to almost the complex structure, let's say integrable complex structure on F. Okay, and then so this gives you at least a zero section. Not a zero section, but you get, once you assigning boundary values, gives a unique zero section lift. I'm using this kind of roughly, and what I mean is constant, so boundary conditions which are, we'll say, constant in the LF variable. Okay, so you get these nice, you actually get a nice lift, and then you can sort of perturb it to some other perturbation structure that you sort of chose before, and you know exactly at least how many vertically constant ones there should be. So that's L is lift to vertically constant by Donaldson, perturb to chosen perturbation data. Say almost complex structure. Okay, and this lift's going to be, it's going to be regular because essentially it's a product of a disk in the base with a constant disk in the fiber, and we already have regularity for constant disks. I think I'm going to stop there.